Hello and welcome back to Calculus 1, section 3.8 on implicit differentiation. More derivative techniques, right? Now this one is really special. It's different than all others. Every other differentiation techniques that we learn is going to be applied where you take the derivative of a function. This is the only one where you can take derivative of anything. So we have in mathematics two worlds to worry about. One is the world of a function, which is the f of x, y equals f of x, right? And then we also have the world of a relation, which is else. Well, no, it's not else. It's everything. What's the difference? The difference is that word unique. If you remember the definition of a function, which you had on your exam, and you either wrote it or not, that definition had the word unique, and I told you that's the one that actually carries the definition of the function. If you take that word out, you get the definition of a relation. Then we also talked about the vertical line test and all the ways that, relation would not be a function. And we mentioned a circle as an example of an equation that it's not a function because it fails vertical line test. So if I have a function, I can look, let's say, into x squared, right? It passes vertical line test, everyone is happy, and we are able to write y equals x squared. On the other side, if I draw a circle, this would fail vertical line test because the vertical line would cut it in at least two spots. And the equation for this, let's say 9, clearly has y squared in it. Now you can also go with a sideways parabola, which is x equals y squared. So there are many examples, obviously, ellipse and everything else. Hyperbolas, they all have y squared somewhere. So generally, when you have a y to the even power, you are not getting a function, right? There are other ways in which it can be, it can result in not having a function, but y squared or y to the fourth or y to the even power is guaranteed. Now, if you look at this x squared graph, we know that we can find the tangent line at any point. So you give me an x value, and I will find the tangent line using the tangent line procedure. Now we know that for tangent line procedure, your first thing to do is to find the slope of the tangent line. And to find the slope of the tangent line, you need the derivative. Now, I am able to draw tangent line for a circle. Now, if I have a tangent line, that tangent line has a slope. And if you have a slope of the tangent line, that means there had to be a derivative that gave you that slope. So that means that there is a derivative procedure for that which is not a function. Now, every single one of the procedures that we learned so far was for functions. But now we need something that is not for functions. And how are we going to find that? Well, that's what is implicit differentiation for. But first, before we do that, let's talk about implicit and explicit equations. So, implicit versus explicit. See, if I want to write the same equation in these two forms, over here as explicit I will write y equal x squared. For the implicit form I can write y minus x squared equals 0. There's an example. Another example. Y equal sine x. On the other side, y minus sine x equals to 0. Now, Let me write for implicit side x squared plus y squared equals to 9. On the explicit side, nope. Can't do it. You cannot solve for y, because y, if you do solve for y, you force it, you will get this. And see this problem over here, the plus minus thing, right? Not a function. So you can't write it in the explicit form and do derivatives and calculus and integrals and all this kind of stuff, because x squared plus y squared equals 9 is not a function. So it does have its implicit form. You can move 9 and equal it to 0. It doesn't matter what you do, right? But you can't write it as y equals everything else. And there are many things like that. So I can write xy minus sine y equals to 6. Nope. There is no way to solve this as y equals everything else. It did not include any squares. I told you that there are possibilities of not having a square and still not being a function, right? So in order for this to be a function, it's not enough, but it's at least a good first step, is to write y equals everything else. Like that must be there. And then we can look into other things as well to be satisfied. So now I have an issue of what to do with this, right? Well, luckily we learned the chain rule. You see, what we are going to understand, whether we have implicit function or not, or implicit form or not, at all times we have to observe the good old thing from pre-calculus, that y is equal to f of x. So y is a function of x. And even if I have this, it's still okay, because the y is the function of x, so the first term becomes a product rule between x and f of x. See that? And then I can take the derivative. So if I am to take this in consideration, then this formula will actually state f of x minus sine f of x equals 6. And I'll just say use product rule, chain rule, product rule, chain rule, and I'll put 3 dots. So whatever we learned, right? So what is now in our realm of possibilities? Well, I can take the derivative of x and, as we know, get 1. I can take the derivative of x squared and get 2x. But here's the cool part, and it goes back to the chain rule from last time. I can take the derivative of y, and if I take the derivative of y, I will get 1, but I have to multiply it with a chain rule. Remember that we have to multiply with the derivative? So you can call it y prime, or you can put dy dx. And I can take also the derivative of y squared the same way. It's 2y, but I have to follow with a chain, because I was taking the derivative where these guys don't match. So, and I know that that the y is a function of x. So that's why this piece has to be there. Now, for those of you who want to really dig into this stuff, note that when you are taking the derivative of, let's say, x to the 4th power, you go 4x to the 3, and then you can put dx dx. Because you can say, I took the derivative of x in respect to x. But that cancels to 1, which is the reason why we don't write it. Where the derivative of y to the 4th would be exactly the same thing, so 4y cubed, but now you have to write dy dx because you took the derivative of y in respect to x. That's the chain. But now they don't cancel because they are not the same. So it has to stay. So these are the differences between taking the derivatives of what we are used to so far versus the new stuff, where y is the function of x. And it adds a whole new level of complexity to all of your equations because now you have to worry about what's variable, what's constant, and what's parameter. Right? And those things are, so parameters are still numbers that are adjusted, and derivative of it is, you copy it because it's, right? The constant is the number you add and subtract at the end, like that plus c, right? Which has a derivative to be 0. And then obviously the derivative of the variable. But now you also have to worry about whether the variables match or not. So that's another part. So please observe that the mechanics of taking derivative is the same. Right? You still get 4x cubed or 4y cubed. That's not a problem. Use the same rules. We are not learning new rules. What's new is the chain rule piece has to be added if you are taking the derivative of the variables that are related to a function and are not the same. Now, if I started writing this from day one, and I could have started writing this from day one, this would not be as new, right? Because you would have in your minds, all right, the derivative of x to the 4 is 4x cubed. I took the derivative of x in respect to x. It cancels to 1, so I don't have to write it. Now, that goes for every derivative we ever did so far. I never wrote it. It was always there. I never wrote it out. It was always there. Now we need that piece, and it has to stay because dy and dx, they don't cancel. And it comes from the simple chain rule. I wrote it here in red, that y is a function of x. So when I'm taking derivative of y, I better have that y prime following, and y prime, different way to write it, is dy dx. So now I'm going back to my circle. Right? I have a circle with a radius 3. And I want the tangent line. So my equation is x squared plus y squared equals to 9. It's not a function. I can't write it y equal everything else. Therefore, I can't use any of the previously learned derivative techniques. However, I can use implicit differentiation. And I can use implicit differentiation because, right, I have implicit formula up there, implicit form. So I will say, all right, what is the derivative of x squared plus y squared equals to 9? Well, do it term-wise. What's the derivative of x squared? 2x. And then we follow with dx dx, right, which will cancel. So we don't have to write it. What's the derivative of y squared? 2y. And then we have to write dy dx. Very good. When you take the derivative of y in respect to x, you have to follow with the dy dx. And what's the derivative of 9? 0. It's a constant. Derivative of constant is 0. There it is. That's the derivative. Now you also see the derivative piece. Fish it out. And you will have derivative equal everything else, and that's the derivative. Now, you have your 2y dy dx equals to negative 2x. Then dy dx is equal to negative 2x divided by 2y. Right? When you move 2y on the other side, these 2's cancel, and here's your derivative. Negative x over y. Now you see your derivative depends on both x and y. We never had that before. But again, we never took the derivative of implicit form before either. So that's fine to have something new. So this is the entire process of implicit differentiation. You take each derivative separately, and every time you're taking the derivative of y in respect to x, you have to follow with a chain, which is dy dx. Now later, that chain becomes your derivative equals everything else. So it's not there for decoration, okay? This guy over here is actually this guy here. So we need it. Now, if I give you a point, 1, 7, you will plug 1 and 7, and you get slope of negative 1 over 7. You have 1, 7. So let's say at 0.17. So now I can calculate the slope as negative 1 over 7, because I plugged in x equals 1, y equals 7. And then I have 1, 7 point. So now y equal mx plus b. Y is equal to 7, m is equal to negative 1 over 7, x equals to 1 plus b, from where b is equal to 7 plus 1 over 7, that's 50 over 7. So the tangent line that would touch this circle at 1, 7 is going to be oh, this is actually terrible. I picked a random point. See what I did? I am fixing the circle to be at the origin, and I am fixing the radius to be 3. So the circle is very well defined. This circle doesn't go through 1, 7. This circle doesn't go through 1, 7 at all. If you try it, you get 1 plus 49, you get 50 equals 9. So 1, 7 is a terrible point to pick because it's not on the circle. We actually have to pick something that it's on the circle. So if I'm going to keep 1, I actually have to figure out what y is for 1. So I have 1, 8, so 2 root 2 is something that it's on the circle, or negative 2 root 2. So this has to be 2 square root of 2 in order for it to be on the circle. So now my slope is 1 over 2 root 2. I need to rationalize that. So multiply by root 2, top and bottom. I get negative root 2 over 4. Much better. So now I have to just redo all of this. So I have y, which is 2 root 2, is equal to slope negative 2 root 2 over 4 times x, which is 1, plus b. So I have 2 square root of 2 plus square root of 2 over 4 is equal to b. And b, no coughing, is equal to 8, 9 root 2 over 4. So y is equal to negative square root of 2 over 4x plus 9 square root of 2 over 4. And that would be the tangent line. So I can't pick a random point. It has to be exactly the point that is on the circumference. So now if you are to graph the circle and you are to graph this line, they will touch exactly at the point. Now the graph for this should be, right, that's the origin, and then if this is 3, number 1 is here, so we'll have a tangent line which goes like this, and you see that you have a positive b, which you have a positive b over here. You also see that the line has a negative slope, which you do have a negative slope. So, you know, even from a sketch, you can at least hint that what you did is correct. Now, if you want to know that all the numbers worked out perfectly and so on, you will just graph both equations in, let's say, Mathematica. You'll just say graph x squared plus y squared equals 9, and then you type the whole thing over there. When you graph them both, it will show you the circle and the tangent line. If they touch at 1, x equals 1, that means you did a good job. If they graph a circle and the line is somewhere, you know, on the adjacent screen, then clearly it's wrong. So implicit differentiation also has a tangent line procedure. Chain rule has a tangent line procedure. Product rule, quotient rule, basic derivatives. All of them in chapter 3 have tangent line procedure. Tangent line, as I said, is the most important problem of chapter 3 and one of the most important problems, if not the most important problem of Calculus 1, because it measures the rate of change, which is what we want to study in Calc 1. Now, the rest of the implicit differentiation is a whole bunch of examples for us to practice the mechanic of it. So what is the derivative of x squared y minus 3y plus 6x equals to 17? So you will have to take these derivatives term-wise, one by one. If you have any questions, go ahead. Nice. The first term is the product rule. Yes. So you have to do product rule on the first term because it's function x squared times function y. Yeah. Because the derivative of y is 1, right? So you just have dy dx there. Very good. So let's take a look at this together. We have x squared times y. That's a product rule, right? So we have to use copy the first, the derivative of the second. Derivative of y is 1, so we just have dy dx there. You can also put y prime. I don't like primes because if you write too fast, you might, instead of a prime, you might put a dot, or you might, when you write too fast. So the reason why I write dy dx, it's clear that it's a derivative. So copy the first, derivative of the second, plus copy the second, and then derivative of the first. So now the product rule is done. And that's just the first term. The next term for us is to take the derivative of negative 3y. Now, negative 3y is going to be negative 3 and then dy dx. Plus, derivative of 6x is just 6, and derivative of 17 is 0. So these are the derivatives. And now note that I have two terms with dy dx. And I need to write dy dx equals everything else. So it should be common sense that these are the terms that should stay on the left, and then factor it out, and then move everything else to the right. So what I have is dy dx, and then I have x squared minus 3. And then on the other side, I have negative 2xy minus 6. I take these two terms to the other side because they don't have dy dx, so that I can factor out dy dx. Now, once I have that, I divide by x squared minus 3 to get dy dx alone. I can also factor a negative sign over here and have 2xy plus 6 in parentheses with a minus in front, and then x squared minus 3. We can leave it there. You can use this minus to flip the denominator into 3 minus x squared, and then no negative anywhere. But, at the end, it's like, who cares? This is it. So we have that. Let's find more. Now, clearly, product rule, chain rule, quotient rule, they all work within this. You just have to be very careful anytime you're taking the derivative of y to put the chain rule of a y prime in there. So these are the things that we have to know. Let's work on a few exercises from the book. The first one that we are going to look at is problem. Ooh, that's great. Problem 17. Yeah, I know you can do this and look at the answer, but let's just cosine y squared plus x equals e to the y. So let's find the derivative of this in respect to x. Right, so the first part is the chain rule. Derivative of cosine is negative sine y squared. And then we have to go and write times 2y, right? Because we have to take the derivative of the inside. And still we are taking the derivative of y, which means dy dx. There. And then finally plus 1 is equal to e to the y dy dx. Okay, so now I'm going to move sine to the other side because it has dy dx in it, and I'm going to move that to the right, so I kill the negative there. So 1 is equal to e to the y dy dx plus 2y sine y squared dy dx. And now we're just going to swap sides. That's allowed. So dy dx, and then as a factor I have e to the y plus 2y sine y squared is equal to 1. And finally dy dx is equal to 1 over e to the y plus 2y sine y squared. And that takes care of that problem. Let's see what else. So one more of these. Oh, let me just see something. All right. Find the derivative for, open parenthesis, x squared plus y squared minus 1, everything cubed, minus x squared y cubed equal to 0. So let's take a look at this together. And I'm going to extend this problem into a tangent line problem, because there are some cool things we can do. So first off, we are observing the cube, right? So that means there is a chain rule there, and if there is a chain rule there, that means that we have to do the that as a one term. And then the next one, x squared y cubed, is the product rule. So we have to do that one as well. All right, so we start by saying that the something cubed is going to be 3 of that something squared to begin with. So we have 3 x squared plus y squared minus 1, everything to the second power. And now I have to take the derivative of the inside. Now, the derivative of the inside is 2x plus 2y dy dx. Remember, I took the derivative of y, and I have to follow the chain. So now, that's the derivative of the first parenthesis. And now minus, and I have to do the product rule for this one. So copy the first. Derivative of the second is 3y squared dy dx, because I took the derivative. And then it should be plus, but there is a minus in front, so it's a minus. Copy the second, that's y cubed times 2x, equal to 0. So generally this is where mistake happens, and then the whole thing goes to hell from there. Now observe this expression. This is not really user-friendly to actually fish out dy dx equals everything else. However, if the question is asking you for the tangent line, yay, because you don't have to solve it, right? So I'm going to stop here and not actually work out algebra to solve for dy dx. I'm going to say tangent line at 1, 1. And this is great, because now you can plug all of these numbers in. Every x becomes 1, every y becomes 1, and every dy dx becomes m. Yes? This one? There's a minus in front. So that's why there are these two minuses. Otherwise, both would be plus. Because it's a product rule, right? Product rule is first plus the second, but now because it's a minus, it's minus and a minus. Okay. All right, so I get to now copy the entire equation, but every single x and every single y is going to become 1, and every dy dx becomes m. And then we have a very simple thing to solve. So let's go. 3, 1 squared plus 1 squared minus 1, everything squared, times 2 times 1 plus 2 times 1 times m, right? Minus 1 squared 3 times 1 squared times m, minus 1 cubed times 2 times 1 equals 0. Now we can simplify this. 1 plus 1, so that's 1, so that's 3. So we have 3 times 1. Times, in parentheses over here, I have 2 plus 2m. Minus, this is 1 and 1, so 3m. And then minus 2 equal to 0. So now this is 3 times 1 is 3, so it's 6 plus 6m minus 3m minus 2 equal to 0. And finally, 6 minus 2 is 4, plus 3m equal to 0. M equals negative 4/3. We did not go through crazy algebra to solve for dy dx, because we had the point and we replaced all x's and y's, and dy dx became m. And that was it. So plug in x equals 1, y equals 1, dy dx equals m. Now, to find my tangent line, I have point 1, 1, and I have slope of negative 4/3. I can quickly plug all of that in y equal mx plus b, or the other one, whatever. So 1 equals negative 4/3 times 1 plus b. And b becomes 7/3. So tangent line is negative 4/3 x plus 7/3. That's the tangent line. Right, I already did Desmos graph for this. Aw, I know, right? Math is so sweet. Like you're tangent to my heart. Like you're the one. I really mean the one, right? So yeah, these are equations. You can technically model anything, right? And this is what I said earlier when I meant use software to verify your answer. So anytime you work on a tangent line, it's always the same procedure. Your job is to find the derivative. Now, we learned, 8 different things for derivatives. So product rule, quotient rule, chain rule, implicit differentiation, basic, trig, and E, right? There is going to be logarithmic and all of that kind of stuff. So you might have like 10 different things, like inverse trig, to take derivatives with. But that tangent line procedure is always the same. Your job is to find the derivative and then plug the point in to get the slope. So this has to happen every time you graph your function. We see that this is not a function because it fails vertical line test, right? But it's a relation, and we have implicit formula for that. So, I mean, this is not that difficult to memorize if you are interested, right? You can memorize it and have fun with this stuff. But the important part is when you graph them both together, they have to touch exactly at the point that was specified that the tangent line is at that point, and that's 1, 1. So that would be it. If anyone is graphing this, right? So we should get a heart that goes through -1, -1, +1, +1, and over here it should go through 1, 1. And there should be a tangent line there, right, which is the line that we have. And this is happening at 1, 1 as a point. And that's that. So now the next level, right? How about the second derivative? Right. They become progressively worse, all right? And you will see that. So you start with something that is benign and not like really complicated. But then when you have to find the second derivative of that thing, whew, right, it becomes really interesting. So, circle not that bad. This problem, you should be able to take this derivative without thinking, pretty much, right? Yeah, I know it's a product rule here, fine. But then, these 3 are extremely cheap and easy to deal with. So I would label this as extremely easy problem to do. Yeah, it does have product rule, but still follows into that category. Look at its derivative. Holy nightmare, right? Now take the derivative of that one more time for the second derivative, right? And you see immediately, right? So most of the answers for our implicit differentiation is going to be, right, most of the answers are going to be in the form of some kind of a division, because remember, you pull those dx's together, and then you factor and you divide by it. So pretty much every answer should have division. And then the second derivative, it guarantees at least, right, a quotient rule. Now, clearly you have to always be careful and mindful of y's and xy's, the product rule, and all of those kind of things. So second derivative becomes, something that it's really annoying. Guys, it's not difficult, it's annoying. There is a big difference between difficult and annoying, right? It's just like people, right? Like, you can deal with annoying people, that's not a problem. Difficult people, that's, yeah. So we have the same issue here. So let's take a look at least one of these problems for the second derivative. We'll take something that the book believes it's a good thing to do. Problem 31 through 36. So pick a number before you ninja out. 31 to 36. 35 it is. Thank you. So 35. Nice. We have. We're looking for the second derivative. For e to the 2y plus x equals to y. It looks, decently simple. Let's see what derivatives have to offer. So to get to the second derivative, we have to deal with the first derivative first. So that's going to be this. And then we are going to take the derivative of e to the 2y, which is e to the 2y dy dx, plus 1 equals dy dx. We are going to move e to the other side, so we have 1 equals to 1 minus e to the 2y when you factor dy dx. And finally, dy dx on the first derivative is equal to 1 over 1 minus e to the 2y. So this is our first derivative. I shouldn't be boxing this because that's dramatic. It shows up there as a light. Oh, yeah, this is one of the fun ones. All right, fine. Be gone. You just say, oh. I'm just gonna make it thin. There. It's still the colors. So now I am going to take derivative of this, because the second derivative is the first derivative of the first derivative. So the derivative on the outside, you can denote that as the d squared y over dx squared. That's the notation for the second derivative. I will explain that after the problem. I'll explain it now. So please observe. Look at you have to see this, guys. So you have function y, and you want to take the derivative of it, right? It becomes dy dx. And then you want to take another derivative of that. Right? It's d dx is the instruction. So that's why it's d squared y of dx squared. Does it make sense? So this d is detached from y. The other d is attached to x. Okay? So we know that this was a notation, right? When you put, so that's why the square is on d, not on dy, entire thing. Very good. So that was just explanation for the notation real quick. Now let's go and take this derivative. We have, well, pick your poison. Do you want the chain rule or you want the quotient rule? I want the chain rule, because why would I mess with a huge formula for quotient rule if I can rewrite this as 1 minus e to the 2y to the negative 1 and just use the chain rule? It's much easier, faster, and cleaner than going through the whole procedure for quotient rule that has, right, the two terms on top with a minus and then the term in denominator that is squared and then a whole bunch of algebra following, right? So I'm going to use the chain rule, and that goes anytime you have a number in the numerator, right? It's a chain rule rather than a quotient rule. The saddest part is when if I have derivative of x squared over 3. That 1/3 is just a constant. Derivative of x squared is 2x, right? Quotient rule for 25 minutes. No, right? So think about these things. All right, so we go. -1, 1 minus e to the 2y, subtract 1, so that becomes -2 now, times derivative of the inside, derivative 1 is 0, and derivative of this thing is -e to the 2y, times the derivative of the top, which is 2, and times dy dx. Whew. Spicy. -1 and the negative in front of e, they cancel, so we just have a positive value there. So what do I have in denominator? I have 1 minus e to the 2y squared, and in the numerator I have 2e to the 2y dy dx. Yes, the second derivative is in terms of the first derivative. But the good thing is that you know what the first derivative is, so plug that in now. Plug in from the box. So now I have that the second derivative is equal to 2e to the 2y, and then this is 1 over 1 minus e to the 2y, divided by 1 minus e to the 2y, everything squared. So this will go down and make it into a cube. So 2e 2y divided by 1 minus e 2y cubed. There it is. Ta-da! That's that. So you can practice. The textbook has some awesome problems for tangent lines. If you take a look at the 27, 28, 29, they give you all of these equations that you can work with, and they show you what types of relations, like the graphs, you get. These are not functions, obviously. They fail vertical line test, but they all have tangent lines everywhere, and you should be able to compute those tangent lines at the points that are given. And then as you practice this, when you graph, you should get the graphs that they have over there. And I believe there are 2 more of those. Yep, they're here. So, implicit differentiation, rational exponents. What else do we have? Tangent lines. Yeah, some of these will have multiple tangent lines, so that's another thing, which is interesting. Some of the points, let me see, do they have any one of those? Yes. You see over here on problem 28 in the corner how the line intersects itself? Like you have the same thing happening for infinity symbol or number 8. There are 2 tangent lines there, right? Because a line comes in at 2 different angles at that point. So each one of those will have. So now we're not talking anymore about uniqueness of tangent line, where each point has its own tangent line. Now, if the lines intersect there, right from the graph, then you would have multiple tangent lines And, you know, I can have as many as I want, because we can graph all cool things that you will eventually learn in Calc 2 with the polar coordinates. You can graph a flower, and the flower could have 8 petals. And if you have 8 petals, then it has 16 lines that intersect in one point. That's 16 tangent lines, easy, right? In one point. So the number of petals will tell me how many, right, times 2 lines would intersect at the same point, and then at that point, each one of those, right, the point and the line will give me the tangent line. So if I come up with a flower that has 30 petals, that's 60 tangent lines in that point. So you can do whatever, but as I said, every concept in mathematics upgrades. So yeah, I just said that and brushed it off, but chapter 10 is coming for some of you, and that's in that section, right? In chapter 10, when you do polar coordinates, in calculus of polar coordinates, you will have to find the tangent line, and you might have those points where you have multiple tangent lines. So you can also practice those skills here to some extent. That's the implicit differentiation. Great. Bye.